nitrogen. And the nitrogen has two atoms attached to it and a lone pair. That's what gives it a coordination number of 3. 1, 2, 3 things around it. The lone pair counts as part of the coordination number. And if you have 2 lone pairs on the central atom, they count for 2 things. Now, when you have a coordination number of 3, this is like the base shape of the coordination number of 3, where you have the central atom, 3 sets of electrons around it. Actually, one of them is a double bond, but it doesn't affect the shape of it. But one of them is a lone pair. Now, the shape of the molecule is just defined by the atoms that make it up. So one of these atoms is not really an atom, it's a lone pair. I pluck it out, leaving the toothpick there. I want that toothpick there to remind you that there is a pair of electrons that are there, and that pair of electrons is still repelling these other 2. The dot structure makes this thing look linear. But because of that lone pair on the nitrogen, this is not a linear molecule. I talked about that and warned you about that yesterday. Don't think that the actual shape of a molecule is shown by the dot structure. Usually it's not. And it's not in this case. Don't call this a linear molecule. Does that look linear to you? No. What shape is it? It's bent. It's bent because of this lone pair pushing, repelling those 2 away from it. In fact, this lone pair, when you have a lone pair, the lone pair kind of spreads out more than bonding electrons would. And so because it spreads out, it actually puts a squeeze on these remaining bonds. I don't know if maybe you learned that in Chem 1. So where this bond was 120 degrees, because this is a lone pair repelling and it spreads out, we get about a 2 degree squeeze, additional squeeze, when we have a lone pair. So this, the shape would be called bent. And the bond angle, because of that lone pair there, is going to cut our angle by about 2 degrees. So it's 118 degrees. Now, I left the toothpick in there. Really, if I take the toothpick out, we just have to know that it's in there. And that's representing a pair of electrons. So they're spreading out, putting the squeeze on those, so we get a 118 degree bent molecule. Questions about that? We're yet to see another. There winds up being 2 bents, so be ready. You're going to have another bent. And be careful because the 2 bents are not the same angle. We move now to the next coordination number of 4. So I'm going to put these back. The first example of a coordination number of 4 is methane, CH4. Methane, if you're ever asked what is the bond angle in the methane molecule, don't just do the dot structure and assume that it's 90 degrees. It's not. 90 degrees is wrong. The dot structure makes it look like it, but the CH4 is a 3-dimensional molecule. They can spread out more than 90 degrees, and that's what we rely on Vesper theory for, is to give us a picture of the atom where the central atom has all of its electrons as far from each other as they can get. Now you know what this looks like. As far as they can get is going to have that shape to it. This shape. And what do we call this shape? This is a tetrahedral shape. Yeah. Tetrahedral is kind of like a tripod in which no matter what way you orient it, you're going to have one bond going straight up and the other 3 kind of going down as the base of a tripod. But if we connect these peripheral H's with imaginary lines, we would see that there are 4 faces on it. Even the bottom would represent a face. They're all triangular in shape. That's where we get the name tetrahedral from. You got a face there, 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 and there. So, shape is tetrahedral. And then the bond angle, remember what the bond angle for tetrahedral is? 109.5. Yeah, very good memory. 109.5. Yeah, when you take physical chemistry in the 3rd year of college, you actually have to do the calculus and figure out it's 109.5, which it works. I wouldn't be able to do it anymore. It's been too long. I've forgotten all that physical chemistry and how to do 3D calculus. I remember at the time, though, it was pretty interesting. Okay, so there's our coordination number 4. That's like the base shape of coordination number when it equals 4. The next example would be the ammonia molecule, Nh3. The nitrogen in the middle is going to still have a coordination number of 4. The dot structure looks like this. Three bonded atoms and one lone pair make it a coordination number of 4. So the orbitals in the nitrogen, the black one being nitrogen this time, has 4 electron pairs, all pushing apart from each other as much as they can. But one of them is a lone pair. So if I just remove one of these atoms, remember the shape is just defined by where the atoms are. So you have a pair of electrons there that's not binding to anything. I'm going to go ahead and pluck it out. You just have to remember that it's there. And so that's there, which pushes these other bonded pairs down. Pushes them down like this, which gives us a pyramid shape. See how it's a pyramid? The nitrogen is not in the same plane as the other. Now, if that lone pair wasn't there, it would flatten out and there would be a planar molecule. But it's there. So this is where we get the trigonal pyramid shape. Trigonal meaning it's got a base that's got 3 sides, and then it's pyramid shape, meaning that they're not all in the same plane. Trigonal pyramid. Now I do specify trigonal pyramid because later on we're going to see another pyramid. So that one's not going to have a 3-part base. So we have to know that this one is a trigonal pyramid. Okay, what did we learn before about the lone pair? The lone pair up here spreads out some and it puts a squeeze on the remaining bonds. How much of a squeeze? About 2 degrees. Right. So where we have an angle of about 109.5, make one of those a lone pair and it's going to spread out. And now the angle in the ammonia molecule is about 107. A 2-degree squeeze for every lone pair. And that's what I am saying down here. Note the lone pair takes up a little bit more space than a bond. So it spreads out, putting the squeeze on the remaining bonds. One more shape in the coordination number of 4. That's our good buddy, the water molecule. So water is arranged like this. The dot structure shows the H's at a 90-degree angle. They are not in reality. The oxygen has 2 lone pairs on it. So there's one of the lone pairs, and then I got to pull another hydrogen off. Yeah. You got the oxygen in the middle with a lone pair here, a lone pair here, and so it's got 2 orbitals that have bonds to hydrogens. So the shape of the molecule, if I just go ahead and remove those, we have to remember they're there, but if I take them out, we're left with the shape of the molecule. If I turn it up like that, shape, it's bent again. Yeah. Because those lone pairs there, the water is not linear. Now, what is the angle that this molecule is bent at? This time, we now have, where is that? We got 2 lone pairs. There's a lone pair there and a lone pair there. So we get a squeeze of about 2 degrees per lone pair. That makes the water molecule's angle about 105 degrees. Is that what you said? Nice. Yeah, so that's pretty well documented. Textbooks everywhere say that water's angle is about 105. Even though it was kind of, not kind of, it is the same coordination number as the methane molecule, which has 109.5. Because of those, the spreading out of those lone pairs puts the squeeze on the bottom. All right, moving on. Okay, so you've seen all of those shapes. Now we're going to get to some shapes you have never seen before, unless you study chemistry independently. Coordination number of 5, where your central atom has 5 things on it. Now we didn't do this in Chem 1 because Chem 1 we kind of stuck to the octet rule. PCl5 looks like this. You got a phosphorus in the middle with 5 Cl's around it. Like that. Now, if it's okay with you, I'm not going to put all the lone pairs around the Cl's. They're there. You okay with that? What shape are these going to make? It doesn't make a pentagon because that would assume that it's all two-dimensional. It's flat. The atoms can spread out more than just making a pentagon shape. Here's the shape that the PCl5 is going to make. Now this one's going to be different. Because we've got a lot of atoms to account for, this is the shape that these atoms are, the 5 chlorines around the P are going to have. You got the phosphorus is in the middle. You've got a chlorine above and below, so those they're perfectly vertical. And then you got 3 along a plane that's perpendicular to the line. The line of the first 2 chlorines. So you got 1 above and below, and then 3 that are in the perpendicular plane. Now, what are we going to call this shape? Here's a picture of PCl5. Above, below, and then 3. I call these 3 along the waistline. If you think of this 3-membered line as like a snowman, these 3 are kind of in the waistline of the snowman, like the belt line. Okay? The shape of this thing would be considered, and it's kind of scary at first, but you can make sense of it. It's a trigonal bipyramid. And what that means is this. If you imagine these 3 green atoms in the middle, they're making a triangle above them to that, and they're making a pyramid above, and then they're making a pyramid down below them to the bottom chlorine. It's a trigonal bipyramid shape. And that's what we have here. I haven't made a perfect model of this thing, but yeah, we got a pyramid above and a pyramid below, upside down. Trigonal bipyramid. So that's what the shape we're going to have if we have a coordination number of 5 in the central atom and there's no lone pairs on it. What are the bond angles? What's the bond angle of this right here? It is 90. Yeah, it's right on 90. Yep. Because this plane is perpendicular to that line of the 3 in a row. So we got 90-degree angles plus, what's this angle right there between those along the waistline? It's easy. Those. They're 120 degrees, yeah. Just like in the middle of this thing is a trigonal plane shape. So there's our bond angle of the trigonal bipyramid is 90 and 120. Normally, for the bond angle, we leave the 180 off. But yeah, you do have the 2 that are 180 degrees apart from each other. We just say 90 and 120. Okay, so that would be the shape of PCl5. You got more atoms in there, and they have to arrange themselves like that. Now, for the next one is going to be a little bit weird. TeCl4. Te is underneath oxygen. It's tellurium with 4 Cl's on it. But if we do the dot structure of TeCl4, we're going to come up with this. There's Te, Cl, 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 and Cl. But then we still don't have enough electrons, even when we add the lone pairs around the Cl. So we need 1 more pair of electrons. It's got to go on the Te. Any added electrons have to go on the central atom. So the Te has a coordination number of 5. It's got 4 bonded atoms and 1 lone pair. What is the shape? What that means is we need to take the coordination number 5 and we need to pull an electron, not an electron, an atom off. Well, it turns out that we'll pull off one of the atoms along the waistline. That maximizes the space between the atoms better than if we take one of the ones above or below. So what is now the shape? To me, the shape of this thing looks like a snowman that's about to give you a hug. See it? You got the 3 there, and then it's got its arms out like, oh, hug me, hug me. But the chemists that came up with shapes of molecules were not